leverage what we've learned about hydraulic fractures, how we think that these grow in the subsurface, how to represent those conceptually, and how to then take that and transfer that into demonstrable results in the field. And I spend a lot of time thinking about this because my full-time job is trying to model and represent hydraulic fractures in the subsurface. So why does it matter that we can describe what hydraulic fractures look like and how they are working in the subsurface? And what I've done is I've just pulled a variety of headlines here from across the world where not only in the United States, but now globally, hydraulic fracturing is being looked at as one of these primary drivers of subsurface development, not only in oil and gas, but also in geothermal and carbon sequestration as well. And in order to adequately engineer these systems in the subsurface, we need to understand how the rock is breaking, how these fractures grow, and how we can manipulate and engineer these systems to our advantage. And one of the clearest examples of this is an optimization that I'm taking from a paper we wrote last year on optimization of shale development. This is an example from the Permian Basin. But this is showing for the same well pad in the same position, the optimal development strategy is a function of price. So as oil price increases or the commodity price increases, greater interference between wells is tolerated because we're recovering our revenue at the front end of the production period. And so understanding how these wells are going to interact and being able to characterize, if I drill these wells closer together, what is the degradation of performance I'm going to realize is incredibly important to understanding then what is the optimal strategy. And so what I've done is I've summarized what I think are the three primary learnings that we have taken away over the last 5 or 10 years in the unconventional industry. First, fractures are large. They propagate in a planar manner, and at a large scale, those are very straight features. Within those features, they are more complex. We'll talk about some fracture strands and swarming that we've observed in some of these core 3 studies, etc. Secondly, fractures mostly do not alter the matrix permeability. When we start to understand how large these fractures are and reconcile with what that means in terms of productivity, we end up with solutions that we are producing from the initial virgin rock permeability. And thirdly, fractures take the path of least resistance. We see coalescence and convergence in the far field as well as in the near field. So starting with fractures are planar. Fractures propagate along the azimuth of maximum principal stress. It can be thousands of feet long and vary in height as a function of stress profile, but can be thousands of feet tall as well. So what do I mean when I say SH max or maximum principal stress? Any point in the subsurface, the stress state can be resolved into 3 principal directions. Generally, you have your vertical, maximum, and minimum horizontal stresses. In most of the world, your minimum stress of these 3 component stresses is in the horizontal direction. That's being shown here in a stress map from Snee and Zobak, where it's only in this purple region on the far right-hand side of the scale where you'd end up in a reverse faulting regime where your minimum principal stress is no longer in the horizontal direction. And we can see that that very rarely occurs, but there are a few areas where it does. So what that means is these fractures are typically oriented in a vertical orientation. But then we have this question of how do they propagate once you start cracking around this vertical feature, where does it go? And this is a nice
umekaa na waandishi wa habari unaojihojiwa hapo wewe kuona hata waandishi wa habari wanakubeba.
Watu wana hasira za maisha.
some
Mtu ana hasira
strands
za
arrayed
maisha anakuja kumalizia mtaani.
to then what has been called complex fracturing or complex fracture networks, where you have branching and shattered glass. And back in the early 2000s, when unconventional developments first started gaining momentum, particularly in the Barnett, this was a study that came out from Fisher et al. In 2002 that showed when they stimulated this well in the, as indicated by this black circle, it's a vertical well, they saw these microseismic events, and the researchers were able to then kind of draw these conjugate pairs of all these lines and claim that this was evidence of complex fracturing or complex fracture networks. And then we started getting horizontal wells and looking at, again, microseismic activity. So microseismic is looking at noise in the subsurface caused by shearing of the rock. And we developed this conception that we have these relatively short fractures that we're developing in this complex manner. So you can, again, draw different line segments through here to represent this nest of intersecting fractures. However, in the last 5 years, we've developed new technology in the subsurface, namely the use of fiber optic cables to measure strain. And so this is a paper from Ugueto et al. At Shell that nicely shows what these fiber optic acquisitions are measuring. So if you have a hydraulic fracture propagating through the subsurface, this would then be a horizontal observation well. As those fractures cross the observation well, you get an extension in that cable, which manifests as a strain and is measured up at the surface. And then as that fracture closes, you get a compressional event, and so you get this series of extension and compression signatures across that observation well. And what we start to see is very discrete individual fracture crossings all along the same corridor. And so this is a paper from Apache that we wrote with them, looking at the characterization of fracture length versus time, and the way that we're able to reconcile that in a model and replicate these fracture crossings as indicated by their circles and diamonds is through the representation of a simple planar fracture. And you could argue between the simple and the complex here, but largely these are propagating in the direction of SH max or maximum principal stress. We have the modeled fracture lengths here as the lines. You can see that we can calibrate those to fall within the distribution of those points. Furthermore, in that same study, we looked at this strain event. If you had a fracture crossing or the extension and compression event on a fiber, can you then actually back out what the azimuth of that crossing is? And mathematically you can. There's a different signature here as it crosses that fiber. And indeed, when we investigate all of those fracture crossings across the fiber, they are all in the same azimuth. Again, evidence that these are all propagating in the same direction, directly along maximum principal stress. And then finally, there's been a wealth of these fiber studies now over the last several years. And in particular, when things like stage length are investigated, and this is one coming from Hess in the Bakken, there is a tight correspondence between the length of well that you stimulate and the length of strain or deformation that is seen on the offset well. So when fracking a 400-foot stage, you see a 400-foot wide region of strain on your observation well, 300-foot wide stage, and 300-foot wide area of stimulation on the observation well, 200, 200, etc. So all of these point to having very planar fractures that propagate in the azimuth of SH max. And finally, now we have evidence in the vertical direction as well, where people have started drilling vertical wells within pads. And this is an example from HFTS2, which is in the Permian Basin. with a vertical well that was drilled in the middle of a 4-well horizontal pad, and looking at the strain response of those stages that are fracked adjacent to the vertical well. And they observed over 1,500 feet, and in fact up here this is about 1,800 feet of height extension of these fractures. So not only do we know that these fractures are crossing thousands of feet away, but they're also growing up to 2,000 feet above where the horizontal wells are landed. And just purely from a mass balance, you need planar features in order to replicate those features in the subsurface. So see, if you had things going like shattered glass through the subsurface, it would stay all confined near the wellbore. Second point is that natural fractures may accelerate leak-off, contribute to the system overall permeability, but we don't see any evidence that when you're hydraulically fracturing, you're actually changing the permanent permeability of the rock matrix around those fractures. So we're not getting the stimulated rock volume where we're actually altering the innate rock properties, but instead we're connecting a low permeability system with these highways that are our hydraulic fractures. So one of the best pieces of evidence for this is a recent development from Exxon in the Bakken. So they took their stimulation and producing well here in green. They fracked it as they normally would with multiple stages. But the difference here is they had 2 monitor wells. So they had a well in the same elevation plane, but at an oblique angle, such that they could measure the pressure drawdown at different distances horizontally away from the producing well. And again, they had a similar well below. So they can map what the depletion is both horizontally and vertically away from these hydraulic fractures. So they're doing so here with different gauges, and the conclusion is that wells can drain laterally several hundred feet away along fracture azimuth and downward from the first and second benches of the Three Forks, which is going to be several hundred feet below the green well here. So we know that these wells are actually draining from relatively far distances away from the producing lateral. And then if we combine that with this study from Conoco, Ratterman et al., what they did is they had a well that they stimulated, and in an open hole well adjacent, they mapped all the fractures with an image log they saw across that horizontal observation well. And this image is showing in gray all of the fractures that they mapped across that lateral, and then in black is what they deemed as conductive hydraulic fractures, those that had evidence of hydraulic fracture fluid or proppant inside those fractures. And then these orange dots are pressure gauges across that lateral, and when you take a look at the pressure in those orange pressure gauges as a function of distance from
anataka kunipiga
the
kipengele
black conductive
muda wote
fractures,
hajawahi kunicheki, sasa hivi ndo ananicheki. Kuna wadau, unajua watu
Ah,
wakishakucheki anajua huyu anashika
kamda kale.
kamda kale, anakuja wakati
from those black
I say.
conductive features. So we know that we're draining from very far away, but that drainage is predominantly coming from these conductive features rather than in a generalized sense around each of those fractures. And then final learning here, number 3 on my list, was that fractures will take the path of least resistance. So if a flow localization opportunity exists, fractures will take it. We have traditionally counteracted that by the application of extreme limited entry. This is increasing the back pressure in a completion stage, and in doing so, more evenly distributing fluid between the exit points in a well completion. The nuance here is that if we get too close together, we might start short-circuiting this. So again, this is another paper from Conoco where they did what they call pump down diagnostics. So at the beginning of each completion stage, they would perform a test to understand whether that stage was isolated from the prior stage, and then they mapped that versus the cluster spacing. So what we see is that when the cluster spacing gets too small or too tight, regardless of the limited entry and whether you're diverting fluid out of all of those perforation clusters, there is still a pathway to communicate back through to the prior stage, likely through some sort of axial fracture or cement integrity issues. So what I'm showing in this little cartoon in the bottom right is you might have a fracture that initiates directly from the hole in your pipe or your perforation cluster, but there's also a pathway outside of that pipe or in the annular region where fluid could exit from two different perforation clusters and then coalesce into one fracture as it propagates again in the direction of SH max. So, in summary, the three main points on how fractures are propagating and how we represent those: we want to represent them as largely planar features. Plenty of evidence that these are propagating in the direction of maximum principal stress in the majority of basins. There are isolated examples of nuance here or exceptions. Second, fractures mostly do not alter the matrix permeability. Natural fractures and matrix perm probably reacts somewhat to the high pressure during hydraulic fracturing, accelerated leak off, etc. But when we get to depletion, what the evidence points to primarily depletion from discrete conductive fractures in the subsurface, and fractures are going to take the path of least resistance. So let's take a look at how we apply these principles, starting with that third one of the path of least resistance. This is coming from the SPE data repository, which you can find online on the data on the SPE website. It's a refrac in the Eagleford. What we did is we history matched the first 3 years of production. So here the dashed trends are the actual data that's available on the SPE repository along with the completion and geologic information. The solid lines here are our modeled data. So you see a tight match to that initial productivity period. At year 3, this well is then refractured. So if we have our initial completion, we generate fractures and then produce. This was a cemented liner refrac. So what that means is they place in a liner inside of the initial casing. They then cement around that liner to seal off the annulus between the two well bores, reperforate, refracture, and then produce once again. If we apply those same model parameters to this primary period, as we do to the refrac period, you'll see that we overpredict the productivity of this system by 17 to 20%. And the reason there is that we are generating a lot of new fracture area. So these longest fractures here are the primary fractures that were generated during that initial completion at time 0. When we go in and we refrac, you can see we generate a tremendous amount more of fracture area. However, referring back to that Conoco study, we know that there could be crossflow if you get clusters too close together, or a pathway in which fluid can exit one perforation, go around, and deviate into a different fracture. And so if we apply that principle, here are those primary fractures. We go into depletion, you see that pressure drawn down. Now as we come to refracturing, you can see that we can repressure those primary fractures and divert some of the fluid, lowering the efficiency of that refrac, and as a consequence, generate less fracture area. So after I apply those same cross-flow principles to my model, we get the image here in the lower right. We see these gaps where fluid has diverted into the primary fractures, and you achieve a less efficient completion on the refrac. As a consequence, we now can match the historical data with a high degree of fidelity. And so what this is pointing to is that if we're able to control this, right? If we're able to stop this cross-flow behavior, there could be as much as a 20% upside in productivity of these systems. Second example here comes from that same HFTS2 data set that was exhibiting that very tall fracture growth. In understanding the preference for vertical growth in this particular situation, we can engineer the ideal placement of wells, knowing that the rock is going to rock. We can't change how the rock is going to behave, we can only change how we stimulate it. And so given that very high fracture growth and that energy diversion in the vertical orientation, we found that if we take those same well bores and the same completion design, but actually push them lower within the zone and a little bit closer together, we can more efficiently deplete that subsurface. So in the right-hand side of these images, I'm showing that base case of where the wells were landed and that upward fracture growth. We're seeing proppant stay primarily in that pay zone down here at the bottom, but we do have these gaps in the depletion based on the preference for upward growth. If we take those wells and push them lower in the zone, there is still a propensity for upward growth, but we're capturing more of that pay zone because we've moved the well lower. We're not getting these symmetrical penny-shaped fractures, but instead we're kind of getting these chimneys. So the lower we push those wells, the more fracture area we can keep within the targeted pay zone, which we're showing here on the left-hand side on depletion. Within that pay zone, we're more efficiently, more uniformly depleting that pay zone by understanding how these fractures are going to grow in this particular environment. And third and final example here is on the topic of frackets and parent-child damage. This has been prevalent in the media and literature on our industry. And this comes from an example that we published with Devin, looking at the interaction of multiple wells. So we have a parent well here. Child number 1 is drilled 1 year after the completion of the parent well, and child wells 2, 3, 5, and 6 are drilled 2 years after. Child well 4 is going in the opposite direction, so it's not immediately parallel to the parent well here, if you're wondering why or where child 4 went. What we observe is after 1 year, when this child well is drilled and fracked, the parent well loses about 75% of its productivity. It then produces for another year, and then when child well 2, 3, 5, 6 are completed, it loses another 75 to 90% of its productivity. Again, the dashed trends here are the actual data. The solid lines here are the modeled data. And so the way that we're able to replicate this in a model is through the formation of a conductivity damage within those fractures. So we know that these fractures are forming in a planar manner, propagating in the direction of maximum principal stress. They can interact and intersect within a few degrees, as well as depletion of effects that will pull new fractures into the depleted fractures. And if we just model it like that, we don't get the magnitude of degradation. There is some degradation due to interference, but we don't see the massive 75 to 90% reductions in production. And so we have to introduce a chemical effect to actually constrain conductivity within the original fracture networks. And that's what we're seeing here in this video. This red color is indicative of the damage that is occurring inside of those fractures. It's a function of the pressure, hydrocarbon saturation, and HVFR or polyacrylamide saturation or concentration within those fractures. This was verified by Devin. They did coiled tubing cleanouts. They were able to pull out kind of a gooey substance that a subsequent JPT article referred to as gummy bears, and test that in a lab and figure out what the component analysis was. However, this is not consistent in all basins. So what I'm showing here is the degree of degradation as a function of well spacing in the Permian versus the Montney, and the Montney forms similar to the Stack where the last example came from. And so understanding how these different basins are interacting in this child interaction with the parent and degree of degradation allows us to optimize. You can see here in the Montney, there is far more degradation from an unbounded well all the way down to the tightest well spacing. If this damage is occurring versus the Permian, the degree of degradation is much lower and then imparts a different optimal strategy. So as we think about going forward and how we form a predictive foundation or set ourselves up to be able to optimize, diagnostics, as you saw in the examples that I provided, are key. Understanding how the rock is deforming and reacting to our stimulations. If I were to streamline a diagnostic program, I would try to get DFIDs on as many wells as I can. Sealed wellbore pressure monitoring, or SWPM, on each well pad, and doing interference tests during production. So in conclusion, measuring the subsurface and learning about it empowers our ability to optimize. We can deliver consistent profitability in doing so. We can more optimally recover higher percentages of our resource in place, whether that is hydrocarbon or whether that is heat in a geothermal sense. By understanding how to engineer these systems in the subsurface, we do a much better job of recovering said resource. And finally, we can be better stewards of the environment by right-sizing our completions and understanding what resources are required to bring to location and develop our subsurface resource as well. So with that, your feedback